Welcome to Maths with EJD. In this video, I'll talk about solving quasi-linear and fully nonlinear PDEs. In the last video, I made a kind of introduction to these two concepts. So here we'll be looking at methods of solution to them. Of course, now that we understand the difference between quasi-linear and fully nonlinear PDEs, of course, this lesson will focus on method for solving these types of equations. So we'll have to explore solution techniques for both quasi-linear and fully nonlinear PDEs with worked examples to illustrate each approach. Now, you see, in the last video, I made a table comparing both methods across things like their features, their complexity, and things, and method of solution. So we saw that for quasi-linear, the method of solution is the popular method we know already, which is the method of characteristics. Method of characteristics, where you equate each dependent and independent variable to a particular parameter, which corresponds to the characteristic for the equation. Okay. Then we also have, of course, fully nonlinear. So for fully nonlinear, we saw there that the way to go about it, because of their complexity, we have to resort to numerical methods. We have to resort to numerical methods. Of course, we also have the concept of viscosity solutions coming up. Viscosity solutions, all right, or even some specialized techniques, or some specialized techniques. Okay, so with that in place, let's take let's go for the first one, solving quasi-linear PDEs. Solving quasi-linear PDEs. So this won't be totally new because we've done method of characteristics before. So quasi-linear PDEs are typically more tractable. That is they are easier to solve, right? More tractable than fully nonlinear PDEs. So one of the most common methods for solving quasi-linear PDEs, particularly first order equations, is the method of characteristics. So let's revisit the method of characteristics. Method of characteristics. We already used it in the second video in this playlist. So the method of characteristics is a powerful technique used to solve first order quasi-linear. So if it's not first order, we can't use method of characteristics. So to solve first order quasi-linear PDEs, the basic idea is to reduce the PDE to a set of ordinary differential equations along characteristic curves, along characteristic curves. So let's look at some steps for that. Steps for solving using method of characteristics. Okay, first of all, if you rewrite the PDE, done that before. So here you express the PDE in a form that can be interpreted as a system of ODEs. Number two, you set up characteristic equations. Set up characteristic equations. So here, these characteristic equations are derived based on the given PDE and typically involve the variables x, y, and u. And number three, you solve the system of ODEs. Solve the system of ODEs. Usually, they are very simple systems of ODEs that you can just integrate directly to get results. So solve the system of characteristic equations to find the relationship between the variables. And number four, we can then eliminate the parameter. That's the parameter, whatever parameter you bring in now, which is usually S. So once you have solutions for the characteristic equations, eliminate the parameter to obtain the solution for the original PDE. Okay, so let's switch over to this now while this goes green. So and that comes with an example. So we have example course for quasi-linear. Let me call it example one, while the other will be example two. So consider, I think this particular problem had been treated even in the previous video, in the second video, I think. But I mean, there'll be another perspective to it now. Consider the first order quasi-linear PDE. That is partial u partial x plus u partial y equals 0. So step one, like we've listed up there, step one is to write out the characteristic equations. Characteristic equations. Okay, so the characteristic equations for this PDE are dx ds equals 1, dy ds equals 1, and du ds equals 0. Okay, so the independent variables equate to 1, and then the dependent variable, the derivative of it with respect to that, s is the parameter now, which represent the characteristic. So you equate that to 0. Now, once that is done, you go for step two. Step two, where you now solve the ordinary differential equations. So, first one, from du ds equals 0. Okay. I mean, that's easy because this simply tells us we simply get u to be equal to c1 because the the derivative is 0, so it means it's constant. So we get u equals c1, which is a constant. It's a constant along the characteristic curves. A constant along the characteristic curves. So that goes. And then next we have the x ds. From the x ds, right? From, oh, I thought I just changed this now. From the x ds equals 1, we integrate. So we have dx equals ds, like we've always done. Dx equals ds. So integral of dx equals integral of ds. So that is x equals s plus C2, since we already have C1 before now. So we move on to the next one. So from dy ds equals 1 again. So we integrate. So when we integrate again, we have dy ds. dy equals ds. That means the integral of dy is equal to integral of ds. Again, we have y equals s plus c3. So that's the third one. So next, we now have that from dy ds. From dy ds, right? We know dy ds is equal to, um, we took dy ds to be equal to u. Oh, what did I do here? Sorry. Oh, yeah, this is u. Sorry. Uh, dy ds is equal to u. So what happened? So from the u ds equals 0, we got that. From the x ds, from the x ds equals 1, we got this. Now this should be dy. Uh, okay. Sorry. This should be this should be dy ds equals u because of that u now. So this is dy dx equals u. So dy dx equals u, sorry. So from dy dx equals u, we integrate. So we have dy equals u ds. Okay, so we can integrate now. So we have integral of dy equals integral of u ds. So this gives us y equals, u of course is constant here. So we have us plus c3. That's basically what we have in that case. Okay, so y is us plus c3. And you won't forget that um we already got u somewhere to be c1. Okay, so uh since u is equal to c1, we now have y equals c1s plus c3. So this is what the new value of y is, c1s plus c3. Then we go for the next step. That's step 3. So in step 3, we eliminate the parameter. The parameter is s. We get rid of it because we didn't start with it. So we eliminate the parameter. And how do we do that? Um, so of course, we already have C1 and C3 in this place. So the only thing we have not touched is this expression. Okay. So um from from that expression now, from x equals s plus c2, from x equals s plus c2, okay, we can have that to be s equals x minus c2 because we don't want to see s. Again, we want to replace that s, and that is why we are doing this. So because of that, um, so we can substitute. So we substitute s equals x minus c2 into the equation, for y. So what's the equation for y? This now. Y equals c1s plus c3. Y equals c1s plus c3. Now s is equal to, so s is now equal to x minus c2. So this is x minus c2 plus c3. So if we rearrange that, we have y equals c1x minus c1c2 plus c3. Okay, so we can put all this together to be a new constant c4. So we now have y to be c1x plus c4. Okay, y is c1x plus c4. So that's what y is. But what we actually need, we are actually solving for u. We need u. But we have seen that u is a constant C1. So, but I mean, this helps us to know that y is this value. So if we have initial conditions, we can actually get rid of all this. So now we have what we have like this. So this is what y gives. So let's move on to the next one. Mm, this can now be green while I go for this now. Okay, so let's talk about solving fully nonlinear PDEs. Solving fully nonlinear PDEs. So we know that fully nonlinear PDEs are more challenging. They are more challenging to solve, and often numerical methods, okay, let me emphasize, numerical methods or viscosity solutions, viscosity solutions are required. Okay, so so here, of course, we are going to resort to numerical method because it's not that easy. I mean, there's no closed form way of going about it, like the method of characteristics that we've been using. So numerical methods now. So one of the most, one of the, interestingly, under numerical analysis, I already did some, I already did some numerical method solutions for partial differential equations. So when I get to that point, I'm going to bring in, I'm going to, you know, add some of those videos to this current playlist so we can have everything in one place. So one of the most widely used techniques for solving fully nonlinear PDEs is the finite difference method. Finite difference method. I have videos on this already under numerical analysis, but I'm going to add them to this playlist at some point. So it's the finite difference method. That's the FDM. Okay. The method, this method discretizes. So it turns a continuous function into a discrete function, so to speak. This method discretizes the domain. It discretizes the domain and approximates the derivatives and approximates the derivatives by finite differences. So let's talk about steps. Steps for solving using numerical methods. So we know the key thing here for if you're using finite difference method is discretization. So the first step is to discretize the domain. Discretize the domain. What that means is that you divide the domain into a grid with discrete values of x and y. Okay. So number two, you approximate the derivatives. You approximate the derivatives. Approximate the derivatives. So here, you use finite difference approximations for the second derivatives. Okay. Then number three, you set up the system of equations. Set up the system of equations. So it will now be in terms of matrices. So set up the system of equations. So here, you substitute the finite difference approximations into the PDE to obtain a system of algebraic equations. So that, that would have made it easy to solve, right? Then finally, you solve the system using known methods. In fact, all of these methods have been well explained under the numerical analysis playlist, and I'm going to add the relevant videos there to this, like I said. So use numerical solvers like the Gauss-Seidel, Jacobi, or successive over relaxation. All of these I've done in that numerical analysis playlist. So use all of them to use either of any of them that you of your choice to solve the system of equations. And that's why I'm just going to outline the process here. I won't really go in there because the videos are already there. So which you are going to see. If you can check right away, you can find it already. So let's go for example two. Example two, which is now related to fully nonlinear PDE. So consider the second order. We already know that fully nonlinear PDEs are minimum second order. So it can be second order upwards, but not lower than second order. But we know that quasi-linear PDEs can be are usually first or second order. But fully nonlinear is second order upwards, second and higher order. So consider the second order fully nonlinear PDE, which is partial squared u partial x squared of degree 2 plus partial squared u partial y squared of degree 2 equals 1. So since solving this equation analytically is complex, of course, it's complex. So we use the finite difference method, FDM, for numerical approximation. So for numerical approximation. So, we use numerical approaches when the problem is too difficult to solve, probably when the solution is too difficult or when the problem does not even have an analytical solution in the first place. Okay, so let's go for step one here. Like we said, step one is to discretize the domain. Discretize the domain. So what that means is that you say let the domain be discretized into a grid with delta x and delta y. Okay, then we go for step two. So for step two, you approximate the second derivatives. Approximate the second derivatives. Okay, so using central difference approximations, so we have that partial squared u partial x squared is approximately ui plus 1 comma j minus 2 ui comma j plus ui minus 1 comma j, or like that, all over delta x all squared. Okay, delta x all squared is more like xi plus 1 minus xi all squared, kind of. So we have that for that. So we can also have partial squared u partial y squared to be approximately u ui. So the focus is on j now, uij plus 1, all right, minus 2 uij, all right, plus ui plus ui j minus 1 all over delta y all squared. So we also have this. So this is the finite difference approximation for that also. Then we now go for step 3. So in step 3, we substitute into the PDE, substitute into the partial differential equation. So, and when we do that, we have, so substitute these approximations into the PDE, and then we have ui plus 1 j minus 2 ui plus 1 comma j minus 2 ui comma j plus ui minus 1 comma j all over all over delta x squared, all squared, that was partial squared, u partial x squared, all squared, plus ui comma ui comma j plus 1 minus 2 ui comma j plus ui comma j minus 1 all over partial y all squared, then squared, and that is equal to 1. So with this now, we can break it open and then start solving. But I won't bother about this. Maybe, of course, maybe at other points, maybe I may have to do other methods, but I've already done finite difference method somewhere else. So I'll just leave this one the way it is now and refer you to the video for finite difference method under numerical analysis. Okay. Finite difference method for partial differential equations, that is. So, and then, so with this now, we can, just break it down into matrices and solve. So I'll just go for that step 4. So solve the system. Usually the solution is better with Python code to make things faster. So this results in a system of algebraic equations that can be solved iteratively using numerical methods such as Gauss-Seidel or Jacobi. Okay. So in summary, first of all, we have that quasi-linear PDEs can be solved using the method of characteristics, which reduces the PDE to a system of ODEs along characteristic curves. Then we also know that fully nonlinear PDEs are typically solved using numerical methods such as the finite difference method, FDM, which discretizes the domain and approximates the derivatives. Okay, so with that, again, we come to the end of this video. go ahead, let me know how helpful this video is for you in the comment section. Also, let me know if there's a problem you'd like me to solve or a topic you like me to teach on. Maybe along the line, I'll be able to do that. If you have subscribed already, thank you so much. If you have not, please go ahead and do that because there's a lot here to learn and there's a lot more coming. And um, whether you have subscribed, I mean, if you, as far once you subscribe, please click the notification bell so you can always get alerted each time a new video is released. And be sure to like and share so that more people can have access to this great content we have here. Till I come your way again, keep doing math right. Bye.